capacity. This is another very important term used in thermodynamics. We already know that the heat changes from the system or into the system appear as changes in temperature, isn't it? If a system absorbs heat, then obviously its temperature rises. Similarly, if a system gives its heat, the temperature falls. This is a very normal thing, all of us are aware. The increase or decrease of temperature is basically proportional to the heat transferred. So we can say that Q is equal to a coefficient multiplied by delta T. Okay, Q is equal to coefficient multiplied by delta T, where Q is the heat gained or lost, or we can say Q is the heat transferred, delta T is the change in temperature, and the magnitude of the coefficient depends upon the size, composition, and nature of the system. Now this same relationship can also be written as Q is equal to C multiplied by delta T. Okay, Q is equal to C multiplied by delta T. Now what is this C? The coefficient C is called the heat capacity. Okay, so C is the heat capacity. Now when C is large, that is the heat capacity is large, a given amount of heat results only in a small rise in temperature. Okay, when C is large, a given amount of heat results only a small rise in temperature. But when C is small, then as you can see from this relationship, a given amount of heat results in a large rise in the temperature. Therefore, if we know the heat capacity of a substance, then we can measure the heat supplied by knowing the rise in temperature. Now, you should understand that water has a large heat capacity. Okay, and this large heat capacity of water is responsible for many natural phenomena. Okay, what do you mean by the statement that water has large heat capacity? It means a lot of energy is required to raise the temperature of water. So how will you define heat capacity? The heat capacity is defined as the amount of heat. This is the definition which you have to learn. The heat capacity is defined as the amount of heat required to raise the temperature of the system by 1 degree. Okay? It can be calculated by dividing the heat absorbed by the increase in temperature. Okay? You can see this relationship. The heat capacity C can be calculated how? By dividing the heat absorbed by the increase in temperature. Okay? Now, if Q is the heat absorbed by the system and delta T is the rise in temperature, then obviously C is what? C, according to this, is Q upon delta T. So you can say that heat capacity, in word, heat capacity is equal to heat absorbed upon rise in temperature. So I hope you have understood heat capacity. Now what is the units? Units of heat capacity. Well, if Q is in joules and delta T is in Kelvin or degrees Celsius, then the units of heat capacity are going to be what? Joule per Kelvin or joule per degree Celsius. Okay? Now, the heat capacity is of two types. This is important. Heat capacity is of two types. Number one, heat capacity determined at constant volume, which is abbreviated as CV. Number 2, heat capacity determined at a constant pressure, abbreviated as CP. Okay, so there are two types of heat capacity measured at constant volume, heat capacity measured at constant pressure. Now, how are these two different? Heat capacity at constant pressure is more common than the heat capacity at constant volume. Why? Because it is due to the obvious reason that whatever we do in an open, that is at constant pressure of 1 atmospheric pressure. So obviously CP is more common than CV. Now for solids and liquids, there is not much difference between the values of CP and CV, because in case of solids and liquid there is no effect of pressure. But for gases these quantities differ. Okay. Now we have understood that the heat capacity is directly proportional to the quantity of the substance, isn't it? So more heat is required to raise the temperature of a large sample of a substance by 1 degree Celsius than what is needed for a small sample of the same substance. In other words, you can see larger the sample, greater its heat capacity. Therefore, it is very common to use the two other terms, that is called a specific heat capacity or a specific heat. So this is another term, a specific heat. Heat capacity is different thing, a specific heat is different thing. So what is a specific heat? Well, a specific heat is defined as the heat required to raise the temperature of 1 gram of a substance by 1 degree is called a specific heat capacity or simply a specific heat. Do you understand? The heat required to raise the temperature of 1 gram of a substance by 1 degree is called a specific heat capacity or simply a specific heat. So here the amount of the substance has been fixed to 1 gram. So a specific heat is equal to heat absorbed upon rise in temperature into mass in gram. Okay? So a specific heat is equal to, this is the formula, heat absorbed upon rise in temperature into mass in gram. So what is the unit then? The units of a specific heat are joule per Kelvin per gram. Okay? Or we can say joule per degree Celsius per gram. Then we have another term. The another term is called molar heat capacity. Okay? Molar heat capacity. What is this molar heat capacity? Now, as the name implies, molar heat capacity means heat capacity for 1 mole. So, how will you define it? The heat required to raise the temperature of 1 mole of a substance by 1 degree is called molar heat capacity. This is the definition which you have to learn. Now, what is the formula then? Molar heat capacity is going to be heat absorbed upon rise in temperature into molar mass. Units, the unit of molar heat capacity are joule per Kelvin per mole. Okay. So I hope you have understood these three terms very clearly. One was the heat capacity, other was a specific heat, and the third was molar heat capacity. Now, this is another very important formula. If we know the mass of this substance, its a specific heat capacity, and the rise in temperature it undergoes during the experiment, then the heat supplied to it may be calculated using the formula heat supplied is equal to mass in gram into a specific heat into rise in temperature. So this Q is equal to M into C into delta T. Cs is a specific heat capacity or a specific heat. So this is a very, very important relationship, okay, which will be used in solving the numerical problem. Q is equal to M, C and delta T, where M is the mass, C is the specific heat capacity and delta T is the rise in temperature. Now let us discuss another thing, that is relationship between Cp and Cv. Okay, relationship between Cp and Cv. Well, we have already discussed the two heat capacities are not equal. Cp is greater than Cv. Now let us find out the relationship between Cp and Cv. You know, at constant volume, heat absorbed Qv is going to be Cv into delta T is equal to delta U. We have already done the enthalpy change is nothing, internal energy change. Qv is equal to internal energy change. At constant pressure, heat absorbed Qp is equal to Cp multiplied by delta T is equal to delta H. The difference between Cp and Cv can be derived for an ideal gas. You know, for 1 mole of an ideal gas, delta H is equal to delta U plus P delta V, or delta H is equal to delta U plus delta RT. Okay, delta RT is equal to delta U plus R delta T. Therefore, delta H is equal to delta U plus R delta T for 1 mole of an ideal gas. Now, if we substitute the values of delta H and delta U, then we can find that Cp delta T is equal to Cv delta T plus R delta T. Or Cp becomes Cp is equal to Cv plus R, or Cp minus Cv is equal to R. Now Cp minus Cv is equal to R, very important relationship, but this is for 1 mole of an gas. Cp minus Cv is equal to R, this is for 1 mole of an ideal gas. For n mole of an ideal gas, it is going to be Cp minus Cv is equal to nRT. So this is the relationship between Cp and Cv.